What if I told you the universe is its own greatest architect, that across the vast emptiness of space, without blueprints or builders, it crafts galaxies of breathtaking complexity, all by following simple, hidden rules? This isn't science fiction. It's the astonishing reality of self-organization, the universe's silent genius for turning chaos into cosmos. Picture this: trillions of tons of gas and dust, scattered like fragments of a cosmic puzzle, somehow pulling themselves into spiral galaxies, each one a masterpiece of gravitational artistry. How does something so disordered become so perfectly structured? The answer lies in the universe's ability to orchestrate itself, a dance of matter and energy so precise, it puts human engineering to shame. Think about the last time you saw a flock of birds moving as one, or watched a murmuration of starlings twist and turn in perfect harmony. That's self-organization in action: small, simple parts following basic rules to create something far greater than themselves. Now scale that up to galactic proportions. Imagine clouds of interstellar gas, billions of times more massive than our sun, swirling and collapsing under their own gravity, spinning out delicate spiral arms like cosmic pinwheels. These aren't random accidents. They're the result of fundamental forces working together, a symphony of physics where every particle plays its part. And here's the most mind-bending part. The universe has been doing this since the beginning of time, building galaxies without a single guiding hand. But how? What invisible laws govern this grand construction project? That's the mystery we're unraveling today. From the enigmatic pull of dark matter, the universe's hidden scaffolding, to the delicate balance of gravity and motion that shapes every star and planet, we're diving deep into the mechanisms behind galactic formation. We'll explore how tiny fluctuations in the early universe snowballed into the vast structures we see today, and why self-organization might be the key to understanding not just galaxies, but the very fabric of reality itself. By the end of this journey, you'll never look at the night sky the same way again, because once you see the universe as a master builder, tirelessly crafting order from chaos, you'll realize the cosmos isn't just out there. It's alive with creativity, and we're here to witness its greatest works. Self-organization is nature's quiet rebellion against chaos, a phenomenon so powerful, it builds galaxies without a blueprint. Imagine a construction site where every brick knows exactly where to go, where concrete mixes itself into perfect walls, and steel beams arrange themselves into soaring towers. That's essentially what happens in the depths of space, just on an unimaginably grand scale. Take a spiral galaxy like our Milky Way. Its elegant arms, packed with stars and gas, didn't form because some cosmic architect drew up plans. Instead, trillions of particles follow just a handful of simple rules. Gravity pulls matter together, rotation flattens it into a disk, and turbulence sculpts those iconic spiral patterns. What makes this process so extraordinary is how universal it is. The same principles that shape galaxies also govern snowflakes forming symmetrical branches, or ants building intricate colonies without a foreman. In each case, countless small parts interact locally, following basic physical laws, yet somehow produce global order. For galaxies, the recipe starts with tiny density fluctuations left over from the Big Bang, imperfections so slight, you'd miss them in a cosmic photo. But over billions of years, gravity amplifies those faint wrinkles, pulling matter into dense knots that become stars, then star clusters, then entire galaxies. Dark matter, the invisible glue holding the universe together, acts like scaffolding, guiding where these structures form. Scientists call this bottom-up construction, where complexity emerges from simplicity. It's why no two galaxies look exactly alike, yet they all share familiar features. Picture blowing a dandelion seed into the wind. You couldn't predict exactly where each tiny parachute will land, but you know they'll spread in a rough pattern shaped by the breeze. Similarly, while we can't forecast every star's position in a galaxy, we understand the forces that give rise to its overall shape. This cosmic choreography even explains why some galaxies become spirals while others mature into smooth ellipticals. It all depends on how their gas and stars dance together over eons. What's truly humbling is realizing we're seeing this process unfold in real time. When astronomers peer at distant galaxies billions of light years away, they're glimpsing younger versions of these self-assembling systems. It's like finding snapshots of a skyscraper mid-construction, revealing how beams and floors come together. Except here, the builders are fundamental forces, and the materials are the very fabric of space-time itself. This isn't just a story about how galaxies form. It's a testament to the universe's boundless creativity, its ability to write its own rules as it goes along. Gravity is the universe's quiet conductor, orchestrating the grand ballet of cosmic construction with invisible hands. While we often think of it simply as the force that keeps our feet on the ground, its true power lies in shaping the largest structures in existence. Picture a vast cloud of hydrogen gas floating in the void, seemingly motionless, until gravity begins its patient work. Over millions of years, every atom subtly tugs on every other atom, gradually pulling the cloud inward like a cosmic inhale. But here's where the magic happens. As this collapse accelerates, the gas begins spinning faster, just like a figure skater pulling in their arms. This rotation forces the cloud to flatten into a disk, creating the foundation for what will become an entire galaxy. What's astonishing is how predictable this process is, governed by equations written centuries before we could observe it firsthand. Isaac Newton first described gravity's pull, but it took Einstein to reveal its true nature as the curvature of spacetime itself, a fabric that bends around massive objects, creating the slopes that matter naturally slides along. This bending explains why galaxies often form those iconic spiral arms. As stars and gas orbit the center, regions of slightly higher density create gravitational traffic jams, where material piles up like cars slowing behind a truck on the highway. These density waves become the galaxy's architectural features, permanent yet ever-changing patterns in the cosmic dance. Yet gravity doesn't work in isolation. It collaborates with other fundamental forces in ways that would make any engineering team jealous. Take angular momentum. The same physics that keeps a spinning top upright ensures collapsing gas clouds never fully shrink to a point, instead spreading into vast disks where planets can form. Electromagnetic forces then step in, causing particles to stick together when they collide, building up from dust grains to asteroids to worlds. Even the weak nuclear force plays a role, determining how stars ignite their nuclear furnaces to light up these structures. It's this intricate interplay that makes galactic self-organization possible, with each force handling a different aspect of cosmic construction. The precision of this system is humbling. If gravity were just slightly stronger, the universe might have collapsed back on itself immediately after the Big Bang. Slightly weaker, and matter would never have clumped together at all. Instead, we exist in this perfect middle ground where gravity can patiently assemble galaxies over billions of years, yet leave enough space between them for light to travel across the cosmos. Modern telescopes have even caught this process in action, spotting baby galaxies in the early universe that look like messy blobs, proof that even the most majestic spirals start as chaotic clouds before gravity works its organizational magic. Perhaps most remarkably, gravity's architectural plans scale perfectly from the smallest to largest structures. The same math that describes water swirling down a drain also explains how supermassive black holes shape entire galaxies. This universal language of attraction means that while no two galaxies are identical, they all speak gravity's common tongue, a testament to how simple rules, consistently applied, can create infinite variety. As we look deeper into space, we're not just seeing random scatterings of stars, but gravity's masterpiece in progress, a work of art 13 billion years in the making. Imagine trying to build a house without a foundation. No matter how beautiful the walls, they'd collapse under their own weight. That's exactly what would happen to galaxies without dark matter, the universe's invisible scaffolding. We can't see it, touch it, or detect it with any telescope, yet its gravitational grip is the only thing keeping galaxies from spinning themselves into oblivion. Here's how it works. Every galaxy we observe rotates so fast that the visible stars and gas should be flung outward like riders on a cosmic merry-go-round. But they're not. Something unseen, something holding 5 times more mass than all visible matter combined, keeps everything anchored in place. That something is dark matter. What makes dark matter so extraordinary isn't just its abundance. It's how it sculpts the cosmos through pure gravitational influence. Picture a mold for a jelly dessert. The mold itself is invisible once the jelly sets, but its shape defines the final product. Dark matter works the same way. In the early universe, slight overdensities in dark matter acted as gravitational wells, pulling in ordinary gas like water swirling down a drain. Over billions of years, these accumulations grew into vast, diffuse halos, ghostly spheres enveloping galaxies, their gravity dictating where stars would eventually ignite. Computer simulations reveal this process in stunning detail. Without dark matter's guiding hand, galaxies would be formless puffs of gas, lacking the elegant spirals and structured disks we see today. Yet the mystery deepens when we ask what dark matter actually is. It doesn't emit, absorb, or reflect light, making it utterly transparent to our instruments. We only know it exists because of its gravitational shadow, the way it bends light around galaxies like a cosmic lens, or how it tugs on star clusters like an unseen puppeteer. Some theories suggest it's made of exotic particles that barely interact with ordinary matter, while others propose our understanding of gravity itself might need rewriting. What's undeniable is its role as the ultimate cosmic architect. When two galaxies collide, their visible stars pass through each other like ghosts, but their dark matter halos interact gravitationally, weaving new structures from the chaos. This invisible framework even solves one of the universe's greatest riddles: why galaxies are distributed in a vast cosmic web, with glittering filaments connecting dense clusters across billions of light years. Dark matter laid this web first, its gravitational whispers creating highways along which ordinary matter could flow. The galaxies we see today are just the visible ornaments hanging from this hidden lattice. And here's the most astonishing part: every time astronomers map the universe's large-scale structure, they're actually charting the shadowy outlines of dark matter's handiwork. It's as if we're deciphering the universe's blueprint by studying the buildings it left behind. The more we learn, the clearer it becomes. Dark matter isn't just a component of the universe. It's the stage upon which the drama of cosmic self-organization unfolds. Without it, there would be no galaxies, no stars, no planets, just a thin, formless soup of particles drifting through endless night. Yet despite its dominance, dark matter remains the universe's greatest unfinished equation. a reminder that even as we unlock the secrets of galactic formation, the cosmos still holds its deepest cards close. Spiral galaxies are nature's perfect storm of chaos and order, where randomness collides with precision to create some of the most breathtaking structures in the cosmos. Take a close look at the Milky Way's graceful arms, and you're actually witnessing a cosmic traffic jam in slow motion. But instead of honking cars, it's stars and gas piling up in density waves, regions where gravity has compressed material like an accordion. These waves move through the galactic disk like ripples in a pond, triggering bursts of star formation wherever they pass, the brilliant blue clusters lighting up spiral arms. Those are newborn stars, ignited when the wave's pressure squeezes gas clouds until they collapse under their own weight. What's truly remarkable is how these density waves persist for billions of years despite the galaxy's rotation. Normally, you'd expect the spiral to wind itself tighter and tighter until it disappears like stirring honey in a cup. But here's the twist: the wave isn't physically attached to the stars and gas. It's more like a standing vibration in the galactic disk, with material continuously flowing into and out of the arms like cars merging onto a highway. This self-sustaining cycle explains why spiral patterns can endure for cosmic epochs, constantly refreshing themselves like a never-ending dance. The recipe for a spiral galaxy requires just 3 simple ingredients: rotation, gravity, and a dash of turbulence. Rotation flattens the protogalactic cloud into a disk, nature's most efficient shape for orbiting systems. Gravity then works its magic, amplifying tiny irregularities into pronounced spiral ridges. Turbulence adds the final flourish, stirring the galactic pot to prevent the disk from becoming too smooth. Computer simulations show this beautifully. Start with a clumpy, rotating gas cloud, hit cosmic fast forward, and watch as gravitational instabilities spontaneously organize into those iconic spiral arms. Yet not every galaxy earns this elegant form. Whether a system becomes a spiral or its football-shaped elliptical cousin depends on its history. Galaxies that experience frequent collisions tend to lose their delicate disk structure, their stars scrambled into random orbits. Others, like our Milky Way, enjoy relatively peaceful lives, allowing their spirals to mature undisturbed. Even the amount of available gas plays a role. Spirals need a steady fuel supply to keep forming new stars along their arms. Run out of gas and the spiral pattern fades like a dying ember, the most mind-bending realization: we're essentially watching a self-repairing machine. When satellite galaxies or interstellar clouds disrupt part of a spiral, gravitational forces gradually restore the pattern, like a pond smoothing out after a thrown stone. This resilience hints at something profound. Spiral galaxies aren't just objects. They're processes, dynamic systems that maintain their structure through constant flux. Every time we photograph one, we're capturing a single frame in a billion-year movie, a fleeting moment in a universe that never stops sculpting itself. Elliptical galaxies are the universe's phoenixes rising from cosmic collisions with a beauty all their own. Unlike their spiral cousins, these smooth, golden-hued giants wear their history in their very shape. Picture 2 galaxies, each with billions of stars, slowly drawn together by gravity's inexorable pull. As they merge, their stars don't collide. Space is too vast for that. Instead, they perform an intricate gravitational dance, their orbits intertwining until the original structures are erased, leaving behind a new galactic entity. The result, a football-shaped swarm of stars moving in every direction, like a beehive shaken by some celestial hand. What's fascinating is how these mergers erase complexity to create simplicity. Spiral arms, those delicate traces of orderly rotation, are the first casualties. As galaxies merge, their once-aligned disks become scrambled, their stars flung into chaotic orbits that cancel out any preferred direction. Yet this randomness isn't true chaos. Over time, the system settles into a smooth ellipsoid, its shape dictated by the same gravitational rules that govern spirals, just with a different starting point. Computer simulations reveal the process in hypnotic detail. Watch two spirals approach, their disks warping like taffy, until their stars form a glowing cloud that gradually smooths into that characteristic oval. The scale of these transformations is staggering. The largest ellipticals, often found at the hearts of galaxy clusters, can contain 10 times as many stars as the Milky Way. Many are also red and dead, their gas supplies exhausted by furious bursts of star formation during the merger, leaving them with aging stellar populations and no raw material for new stars. This explains their golden glow compared to the blue-tinged spirals still busy giving birth to stars. Some even harbor multiple supermassive black holes at their cores, remnants of the original galaxies, slowly spiraling toward an eventual merger of their own. Yet ellipticals aren't just in points, they're cosmic laboratories. Their old stars act as fossil records, preserving chemical signatures from the early universe. Their lack of gas makes them ideal for studying dark matter, since there's no obscuring dust to complicate observations, and their prevalence in dense galaxy clusters suggests they're the inevitable products of a universe where gravity never stops rearranging the furniture. In fact, our own Milky Way is destined to become one in about 4 billion years when it collides with the Andromeda Galaxy. The two spirals will likely merge into a single, massive elliptical. Perhaps the deepest lesson ellipticals teach is that self-organization isn't always about creating intricate patterns. Sometimes it's about finding equilibrium in apparent disorder. These galaxies prove that even the most violent cosmic events follow underlying rules, reshaping matter without ever breaking physics commandments. They remind us that the universe doesn't favor one shape over another. It simply explores all possibilities, letting gravity sculpt whatever form the initial conditions allow. So next time you see an elliptical galaxy in a telescope, you're not just looking at a featureless blob. You're witnessing the aftermath of a billion-year waltz, a testament to how chaos and order are two sides of the same cosmic coin. Interstellar gas is the universe's ultimate recyclable material, a delicate, wispy medium that somehow transforms into the blazing furnaces we call stars. Picture it as the cosmic equivalent of flour scattered across a kitchen counter. Left alone, it's just a fine dust, but add a little moisture, or in this case gravity, and suddenly it clumps together, forming the dough from which stellar loaves will rise. These clouds of gas, primarily hydrogen with traces of heavier elements, don't just float passively through space. They seethe with turbulence, sculpted by shock waves from exploding stars and the invisible threads of magnetic fields that weave through them like cosmic spider silk. What's astonishing is how these chaotic clouds follow an invisible script. Turbulence stirs the gas into intricate filaments, vast, ribbon-like structures light years long, while gravity works patiently to gather material into dense knots. Imagine blowing on the surface of a cup of coffee and watching the creamer swirl into temporary patterns. Now scale that up to a cloud 100 light-years wide, where every ripple and eddy could become the cradle for a new solar system. These filaments aren't random, they're highways of star formation, funneling gas toward regions so dense that not even light can escape their grip once collapse begins. The moment gravity wins its tug of war with gas pressure is when the magic happens. A knot of gas, perhaps triggered by a nearby supernova shockwave or simply grown massive enough on its own, begins to crumple inward. As it collapses, the gas heats up, spinning faster like a figure skater pulling in their arms. At the center, temperatures and pressures climb until hydrogen atoms, which normally repel each other, are forced so close together that they fuse, igniting the nuclear fire that defines a star. But here's where self-organization shines. That newborn star doesn't just sit quietly. Its fierce radiation and stellar winds blow bubbles in the surrounding gas, compressing nearby regions and seeding the next generation of stars. It's a cosmic domino effect, where one birth triggers another in an ever-expanding wave. This cycle explains why stars rarely form in isolation. Open a telescope image of the Orion Nebula, and you'll see hundreds of young stars glowing like jewels nestled in their gas cocoons. Each one is a testament to how local interactions, particles bumping, gravity pulling, radiation pushing, scale up to create structured communities. Over time, these stellar nurseries build the population of a galaxy, with stars of different masses playing distinct roles. The most massive ones burn bright and die young, scattering heavy elements back into the gas pool. Smaller stars, like our Sun, simmer for billions of years, providing stable orbits for planets to form. Together, they transform raw gas into the complex chemistry that makes life possible. The true wonder lies in how these small-scale processes imprint themselves on entire galaxies. Spiral arms, those grand sweeping curves we admire from afar, are essentially traffic jams in the galactic gas flow regions where density waves have compressed the interstellar medium into star-forming frenzies. Even elliptical galaxies, though they've lost most of their gas to ancient collisions, still carry the chemical fingerprints of this cycle in their ancient stars. Every element heavier than hydrogen and helium, the carbon in your DNA, the iron in your blood, was forged in stellar cores or cataclysmic explosions, then scattered back into the interstellar medium to be recycled anew. So when we gaze at a galaxy, we're not just seeing a static collection of stars, we're witnessing a dynamic ecosystem where gas is the currency of creation and destruction. It's a system so finely tuned that the death of one star becomes the birthright of another, a celestial economy where nothing is wasted, and every collapse sows the seeds for new beginnings. The interstellar medium isn't just the raw material of stars, it's the living, breathing pulse of the galaxy itself. Stars are the ultimate cosmic alchemists, transforming simple hydrogen into the heavy elements that build planets and life, then scattering their creations across the galaxy in spectacular final acts. When a massive star reaches the end of its life, it doesn't fade quietly. It detonates with the energy of a billion suns, a supernova explosion so powerful it can outshine an entire galaxy for weeks. But this isn't just a cosmic fireworks display. That explosion sends shockwaves rippling through interstellar clouds, compressing gas like a snowplow piling up drifts. And just like those piled drifts can collapse into avalanches, those compressed gas pockets collapse into new stars. At the same time, the dying star blasts out carbon, oxygen, iron, and other elements forged in its core, seeding future generations of stars and planets with the ingredients for complexity. This cycle of destruction and rebirth is nature's way of balancing the books. Without supernova, galaxies would either exhaust their gas too quickly, turning all their raw material into stars in one frenzied burst, or stagnate, with gas remaining too diffused to collapse. But feedback loops create harmony. Picture a forest where occasional wildfires clear old growth, making room for new saplings while recycling nutrients into the soil. Supernovas serve the same purpose on a galactic scale. Their explosions regulate star formation like a cosmic thermostat, turning the process up or down depending on conditions. When a region gets too crowded with young, massive stars, their eventual supernova blow away nearby gas, putting a temporary stop to further star birth. Meanwhile, in quieter galactic suburbs, shockwaves from distant explosions can reach undisturbed gas clouds, nudging them past the threshold to form new stellar nurseries. The numbers reveal just how precise this balancing act is. In our Milky Way, stars form at an average rate of about 1 solar mass per year, not too fast, not too slow. If the rate were significantly higher, our galaxy would have burned through its gas reservoir billions of years ago. Much slower, and there wouldn't be enough heavy elements to form rocky planets like Earth. This equilibrium exists because feedback mechanisms automatically adjust the system. Massive stars, though rare, wield disproportionate influence. A single O-type star, dozens of times heavier than our Sun, can ionize surrounding gas with its ultraviolet radiation, preventing further collapse. Then, when it explodes, it disperses that same enriched gas back into the galaxy, where it will eventually cool and form new stars, but only once conditions are right. Disrupt this balance, and entire galaxies can veer off course. Starburst galaxies, where star formation runs amok at rates 10 or even 100 times normal, offer a cautionary tale. Triggered by collisions or other disturbances, these galaxies churn out stars so rapidly they risk exhausting their gas within a few 100 million years, a cosmic blink of an eye. The resulting supernova then blow out the remaining gas so violently that star formation may cease entirely, leaving behind a red and dead elliptical galaxy. On the flip side, some dwarf galaxies show what happens when feedback is too weak. Without enough massive stars to drive supernova winds, their gas never gets properly stirred, leading to sporadic, inefficient star formation that leaves most of their potential locked away. What's truly humbling is realizing we're made from this very cycle. Every atom of oxygen in your lungs, every speck of iron in your blood, was forged in the heart of a long dead star and scattered across space by its explosive demise. The same feedback processes that regulate galaxies also ensured those elements found their way into the molecular cloud that birthed our solar system. This isn't just astronomy, it's genealogy written in stardust. The universe doesn't just build galaxies, it fine-tunes them through countless cycles of creation and destruction, each explosion setting the stage for the next act in an endless cosmic drama. Galactic winds are the universe's way of breathing a cosmic exhale that sculpts galaxies with invisible hands. Imagine a candle flame flickering in the wind, its shape constantly reshaped by forces it can't see. Now replace that flame with an entire galaxy, and the wind with million-degree plasma racing outward at thousands of kilometers per second. These aren't gentle breezes. They're titanic outflows powered by the combined fury of exploding stars and supermassive black holes feasting at galactic centers. When hundreds of supernovae detonate in quick succession common in star-forming regions, their collective energy punches holes in the interstellar medium, launching fountains of hot gas that can escape a galaxy's gravity entirely. What makes these winds so fascinating is their dual nature. At first glance, they seem destructive, blowing away the very gas that galaxies need to make new stars. And indeed, in extreme cases, they can quench star formation entirely, leaving a galaxy red and dead. But look closer, and you'll see a self-regulating mechanism of astonishing precision. Just as wildfires clear underbrush to prevent larger disasters, galactic winds prevent galaxies from growing unchecked. Without them, galaxies would gorge on gas, forming stars so rapidly they'd exhaust their fuel supplies within a few 100 million years. The resulting stellar explosions would then leave behind nothing but aging stars and darkness. Instead, winds act like a thermostat, ejecting just enough material to keep star formation at a sustainable simmer. The mechanics behind these outflows reveal nature's ingenuity. As superheated gas expands outward, it sweeps up cooler material like a snowplow, creating vast shells of mixed elements that eventually stall and fall back into the galaxy. This recycling process can take hundreds of millions of years, turning galactic winds into cosmic conveyor belts. Some simulations show these ejected materials eventually raining back down in distant regions, seeding new star formation far from their origins. It's as if galaxies share resources across generations, like trees dropping seeds for future forests. Black holes add another layer of complexity. When matter spirals into a supermassive black hole at a galaxy's core, friction heats it to unimaginable temperatures, creating quasars, the universe's most luminous object. The energy released can drive jets and winds so powerful they push gas out to intergalactic space. These active galactic nucleus and winds often work in concert with stellar feedback, creating a balancing act between destruction and creation. Too little AGN activity and a galaxy might overproduce stars. Too much and it could strip itself bare. The sweet spot lies somewhere in between, where winds from stars and black holes complement each other like yin and yang. On the largest scales, these winds weave the cosmic web itself. As they transport heavy elements into the voids between galaxies, they enrich the intergalactic medium with the building blocks for future structures. Some of this material eventually cools and condenses into new galaxies, while other parts remain as diffuse filaments, the invisible scaffolding of the universe. Telescopes have even caught this process in action, spotting galaxies with winds so massive they trail behind like cosmic comet tails, stretching for hundreds of thousands of light years. Perhaps the most poetic realization is that we're seeing the universe regulate its own growth. Galactic winds aren't accidents, they're an essential part of how galaxies mature and stabilize over billions of years. They transform isolated star factories into balanced ecosystems, connecting galaxies to their surroundings in an intricate dance of give and take. Every time astronomers detect these outflows, whether through the X-rays of hot gas or the spectral fingerprints of ionized elements, they're glimpsing a universe that doesn't just build itself, but breathes, adjusts, and fine-tunes its own evolution. Black holes aren't just cosmic vacuum cleaners, they're master regulators, wielding influence far beyond their event horizons. At the center of nearly every galaxy, including our own Milky Way, lurks a supermassive black hole, some weighing billions of times more than our Sun. While their gravitational pull is infamous for trapping light itself, their true cosmic role is far subtler. When these giants awaken gorging on swirling disks of gas and dust, they transform into some of the most energetic objects in existence, active galactic nuclei. The radiation and particle jets they emit can outshine all the stars in their host galaxy combined, flooding interstellar space with enough heat to evaporate star-forming clouds like morning mist under a scorching sun. This process, called active galactic feedback, is nature's way of preventing galactic obesity. Without it, galaxies would greedily convert all their gas into stars, burning through their fuel reserves in a frenzied burst of youth. But black holes intervene like strict cosmic accountants, balancing the books. As a galaxy's star formation rate climbs, more gas spirals toward the central black hole, feeding its growth. The resulting energy output then heats the surrounding medium, pushing gas away or rendering it too turbulent to collapse into new stars. It's a self-correcting loop. The more a galaxy tries to grow, the harder the black hole pushes back, ensuring long-term stability. The scale of this regulation is staggering. Some black hole jets stretch for millions of light years, far beyond their host galaxy's borders, carving bubbles in intergalactic gas that persist for cosmic epochs. These structures, visible in radio telescopes, reveal how black holes don't just shape their immediate surroundings, they engineer the environment for future galaxy formation. When a jet plows into intergalactic gas, it can trigger shock waves that compress distant clouds, sparking star formation in entirely separate galaxies. One black hole's off switch becomes another's on switch, weaving a web of influence across the universe. Yet black holes aren't always active. They cycle between feast and famine, sometimes going dormant for billions of years. During these quiet phases, galaxies can experience brief bursts of unchecked star formation, like a city lifting its ban on fireworks. The nearby galaxy Messier 87 offers a stunning example. Its dormant central black hole allowed gas to accumulate undisturbed, creating a dazzling ring of young blue stars encircling the dark giant. But this peace is temporary. Eventually, turbulence or a passing gas cloud will funnel material back toward the black hole, reigniting its engine and restoring equilibrium. The most profound evidence of black holes' regulatory role comes from computer simulations. When scientists model galaxy evolution without including black hole feedback, the results look nothing like the real universe. Galaxies grow too massive, too quickly, their stars crammed into unrealistic configurations. Only by adding black holes balancing act do virtual galaxies begin mirroring those we observe, proof that these invisible titans are as essential to galactic architecture as gravity itself. What's truly humbling is realizing how black holes link the smallest scales to the largest. The same physics governing an atom-sized singularity also shapes galaxy clusters millions of light-years across. Their event horizons may mark points of no return, but their influence radiates outward, sculpting the cosmos in ways we're only beginning to understand. They remind us that the universe's most powerful forces often hide in plain sight, silent conductors orchestrating the grand symphony of cosmic evolution. Galactic mergers are the universe's ultimate makeover artists, taking something familiar and reshaping it into entirely new forms. When two galaxies collide, it's not the catastrophic wreck we might imagine. Stars are so far apart that direct collisions are incredibly rare. Instead, their gravitational fields intertwine like cosmic hands, pulling and twisting each other into unprecedented configurations. Picture two vast crowds merging in a plaza. Individuals don't crash into one another, but the overall flow of movement creates new patterns. That's exactly what happens on a galactic scale, where gravity choreographs a slow-motion ballet lasting hundreds of millions of years. The first signs of transformation appear in the galaxy's delicate spiral arms. As mutual gravitational attraction distorts their shapes, long tidal tails of stars and gas stretch outward like pulled taffy, some extending hundreds of thousands of light-years. These spectacular bridges and arcs become intergalactic highways, funneling material between the merging systems. Meanwhile, shockwaves compress gas clouds within both galaxies, igniting fireworks of star formation. The antennae galaxies, captured in stunning Hubble images, showcase this process mid-stride. Brilliant blue clusters of newborn stars speckle their collision zones, while orange dust lanes twist into chaotic ribbons. But the real magic happens in the aftermath. As the merger progresses, the galaxies' once distinct structures blur together. Their stars, now sharing a common gravitational pool, gradually relax into new orbits, trading the orderly rotation of spirals for the random motions characteristic of elliptical galaxies. This transition isn't instantaneous. Computer simulations reveal it as a kind of gravitational relaxation, where the system sheds excess energy through complex dynamical processes. Imagine shaking a snow globe and watching the flakes gradually settle into a new configuration. Over billions of years, the merged galaxy finds equilibrium, its stars distributed into a smooth, three-dimensional ellipsoid. Our own Milky Way offers living proof that mergers aren't apocalyptic events, they're growth spurts. The Gaia spacecraft has mapped streams of stars wrapping around our galaxy like celestial spaghetti, the remnants of dwarf galaxies consumed long ago. One particularly dramatic collision, dubbed the Gaia-Enceladus merger, occurred about 10 billion years ago when a smaller galaxy plunged into the young Milky Way. Far from destroying our galaxy, this event contributed up to 50% of the stars in our galactic halo. Even now, the Milky Way is digesting the Sagittarius dwarf spheroidal galaxy, whose stretched-out remains form a delicate loop around us. What's astonishing is how these violent encounters lead to new symmetries. Post-merger galaxies often exhibit surprisingly regular features, central bulges with precise brightness profiles, or star orbits that align in unexpected ways. This self-reorganization hints at deep universal principles. Given enough time and the right conditions, chaos inevitably gives way to order. The same gravitational rules that govern a single star's motion also scale up to manage the aftermath of galactic collisions, proving that the universe has an innate knack for finding balance. The ultimate testament to merger's creative power lies in the most massive galaxies we observe, brightest cluster galaxies. These behemoths, found at the hearts of galaxy clusters, can contain trillions of stars and span hundreds of thousands of light years. They didn't grow that large through steady star formation alone. Instead, they're the products of repeated mergers, each collision adding more stars and dark matter to their bulk. Their smooth, featureless appearances belie violent histories, like weathered mountains shaped by eons of geological upheaval. Yet mergers don't just change galaxies, they change their environments. The energy released during these events can heat intergalactic gas for millions of light years around, altering the conditions for future star formation across entire clusters. Some mergers even eject supermassive black holes from their host galaxies, sending them wandering through intergalactic space like cosmic nomads. These rippling effects demonstrate that no galaxy is an island. Each collision sends waves through the cosmic web, influencing the fates of countless other systems. Perhaps the most profound lesson from galactic mergers is that destruction and creation are two sides of the same coin. The same forces that tear galaxies apart also seed new stellar generations, and the same violence that erases old structures gives rise to new forms of order. As we watch mergers unfold across the universe, from the mice galaxies with their long tails to the eventual collision between the Milky Way and Andromeda, we're witnessing the universe's relentless drive to reinvent itself, proving that even in the vastness of space, nothing ever truly stays the same. The cosmic web is the universe's grand design, an intricate tapestry woven from dark matter and gas, stretching across unfathomable distances like a celestial neural network. If you could step back far enough, galaxies wouldn't appear as isolated islands but as glittering beads strung along invisible threads, clustered at intersections where filaments meet. These intersections form the web's dense nodes, home to colossal galaxy clusters containing thousands of galaxies, while the spaces between them stretch into vast, nearly empty voids, some spanning hundreds of millions of light years. This structure didn't emerge by accident. It's the result of gravity amplifying tiny fluctuations in the early universe, sculpting matter into a pattern that mirrors the branching of trees or the veins in a leaf. What's astonishing is how this web dictates the fate of individual galaxies. Picture a city's subway system. Your neighborhood's growth depends on whether it's near a central hub or an isolated stop. Similarly, galaxies nestled along dense filaments or at cluster intersections experience a constant inflow of gas, fueling star formation and feeding their central black holes. Meanwhile, galaxies stranded in voids become cosmic backwaters, their gas supplies dwindling as they drift in isolation. The web doesn't just connect galaxies, it shapes their very identities, determining whether they'll become bustling spirals or quiet ellipticals. The web's filaments are more than just pathways, they're rivers of gas flowing toward hungry galaxies. Simulations reveal these streams with stunning clarity. Dark matter's gravitational pull guides hydrogen and helium into narrow channels, which then funnel material toward waiting galactic disks. This process, called cold flow accretion, delivers pristine gas directly to galaxies' outer edges, bypassing the hot, turbulent halos that might otherwise disrupt it. It's like a cosmic plumbing system, with gravity as the water pressure and filaments as the pipes. Some galaxies, particularly in the early universe, grew massive by tapping into these filamentary highways, drinking deeply from the cosmos's reservoirs. Yet the web's influence doesn't stop at feeding galaxies, it also orchestrates their movements. Galaxies don't drift randomly, they flow along filaments like commuters on a cosmic freeway, sliding toward clusters where they'll eventually merge or be torn apart by tidal forces. This galactic conformity explains why neighboring galaxies often share similar properties, from their star formation rates to their shapes. They're not just close by chance, they're siblings raised in the same stretch of the cosmic web, shaped by the same large-scale currents. The voids between filaments tell their own story. These regions aren't just empty, they're underdense to an extreme, with gravitational repulsion actually pushing matter away over time. Galaxies stranded here are like pioneers on a frontier, cut off from the web's resources. Many become red and dead prematurely, their gas stripped away by the void's expansion. Yet even these deserts aren't entirely barren. Some hide ultra-diffuse galaxies, ghostly, star-sparse systems so faint they were only discovered recently. Their existence hints that the cosmic web's influence extends even to its quietest corners. Mapping this structure has been one of astronomy's greatest achievements. Projects like the Sloan Digital Sky Survey have plotted millions of galaxies, revealing the web in 3 dimensions. What emerges isn't chaos but hierarchy, a fractal-like arrangement where small filaments connect to larger ones, which in turn feed into clusters, all nested within superclusters hundreds of millions of light-years across. This pattern mirrors other self-organizing systems, from the neural networks in our brains to the distribution of matter in a foam of soap bubbles. The universe, it seems, has a favorite blueprint. The cosmic web's most profound lesson might be its demonstration of scale. The same gravitational rules that cause an apple to fall also bind galaxy clusters together across billions of light-years. It's a reminder that the universe operates on principles we can grasp, even as it constructs edifices too vast for human intuition to fully embrace. When we look deep into space, we're not just seeing galaxies, we're witnessing the architecture of existence itself, a structure built by time, gravity, and the universe's unshakable drive to organize. Dark energy is the universe's silent rebel defying gravity's relentless pull with an even more powerful push. Imagine inflating a balloon with galaxies painted on its surface. As you blow air in, every point moves away from every other point. Now imagine someone suddenly starts pumping air in faster, making the balloon expand at an ever-increasing rate. That's dark energy in action, accelerating the universe's expansion not just steadily, but with growing urgency. Discovered in 1998 when astronomers found distant supernova dimmer than expected, this mysterious force now accounts for nearly 70% of the universe's total energy content. Yet despite its dominance, we still don't know what it actually is. The most perplexing aspect isn't just dark energy's strength, it's how selectively it operates. On cosmic scales spanning billions of light years, it overwhelms gravity, stretching the fabric of spacetime itself. Yet within galaxy clusters, gravity still reigns supreme, keeping galaxies bound together in tight-knit communities. This cosmic tug-of-war creates a fascinating paradox. Even as the universe expands at an accelerating rate, local structures continue forming and evolving normally. Picture swimmers in a rapidly widening river. While the banks rush apart, the swimmers can still form tight groups, unaware of the changing landscape around them. Current theories suggest dark energy behaves like Einstein's cosmological constant, a steady energy density permeating all of space. But alternative ideas propose it might evolve over time, growing stronger or weaker. Some models even speculate that dark energy could eventually shred bound structures apart in a Big Rip scenario billions of years from now. Yet galaxies and their self-organizing systems show remarkable resilience. Simulations suggest that while dark energy may eventually isolate galaxy clusters from one another, their internal structures could persist far longer than we once thought, gravity's local dominance resisting the cosmic expansion. The cosmic web tells this story in its changing architecture. As dark energy accelerates expansion, simulations show the web's filaments stretching thinner over time, like dough being pulled too far. Galaxy clusters will become isolated islands, their connecting threads stretched beyond recognition. Yet remarkably, this same expansion preserves a fossil record of earlier cosmic epochs. Light from ancient galaxies, redshifted by the expanding universe, carries encoded information about dark energy's influence across billions of years, a time capsule of cosmic evolution. What makes dark energy truly fascinating is how it challenges our understanding of self-organization. Normally, systems evolve toward equilibrium, balancing competing forces. But dark energy introduces an asymmetric element, a one-way push that constantly changes the rules. Yet even here, the universe demonstrates adaptability. Some theorists propose that dark energy's acceleration might actually enhance certain self-organizing processes in isolated regions, like eddies forming in a fast-moving stream. Others suggest that future civilizations might harness the energy of this expansion itself, finding ways to thrive in an ever-accelerating cosmos. The ultimate lesson dark energy teaches is humility. For all our understanding of galactic formation and cosmic structure, the dominant force shaping the universe's fate remains fundamentally mysterious. Every observation, from the distribution of galaxy clusters to the subtle bending of light by the cosmic web, offers new clues about this enigmatic driver of cosmic destiny. As telescopes probe deeper into space and further back in time, we're not just mapping the universe's past, we're glimpsing the unfolding story of its future, one where dark energy writes the final chapters and self-organization adapts to forces we're only beginning to comprehend. Magnetic fields are the universe's invisible puppet masters, threading through galaxies like cosmic marionette strings, gently guiding the chaos of star formation into something orderly. You can't see them, but their fingerprints are everywhere, in the elegant spiral arms of galaxies, the precise alignment of interstellar dust, even the fiery jets erupting from newborn stars. While gravity gets all the attention for sculpting the cosmos, magnetism works behind the scenes, a subtle force with outsized influence. Picture a vast interstellar cloud collapsing to form stars. Gravity pulls the gas inward, but without magnetic fields, that gas would freefall haphazardly, like flour dumped from a sack. Instead, magnetism acts like an invisible scaffold, resisting the collapse just enough to channel gas into orderly streams and sheets cosmic aqueducts feeding star-forming regions with precision. These fields aren't just passive observers, they're dynamic players in galactic evolution. Take the iconic spiral arms of galaxies like our Milky Way. Gravity alone can't explain their crisp, long-lived structure. Magnetic fields, though a million times weaker, provide the extra scaffolding needed to maintain these patterns over billions of years. They do this by aligning charged particles, ions, and electrons into coherent streams that reinforce the spiral density waves. It's like adding starch to fabric. Gravity creates the folds, but magnetism keeps them sharp. Even interstellar dust grains, though neutral overall, become subtly magnetized, lining up like compass needles to create polarized light patterns astronomers can detect. The origins of galactic magnetic fields are as fascinating as their effects. They likely began as faint seed fields in the early universe, perhaps generated by quantum fluctuations during the Big Bang or by the turbulent motions of plasma in the first galaxies. Over time, a process called the dynamo effect amplified these weak fields. Here's how it works. As a galaxy rotates, its charged particles swirl like water in a whirlpool, stretching and twisting magnetic field lines. This motion converts mechanical energy into magnetic energy, gradually building up the field's strength, similar to how a bicycle dynamo turns pedal motion into electricity. The Milky Way's magnetic field, for instance, now averages a few microgauss, about 100,000 times weaker than Earth's, but spanning over 100,000 light-years. Star formation showcases magnetism's delicate balancing act. In collapsing gas clouds, magnetic fields initially resist gravity's pull, slowing the collapse and preventing fragmentation into too many small stars. But as gas becomes denser, particles collide more frequently, breaking free from magnetic constraints in a process called ambipolar diffusion. This allows star formation to proceed, just at a more measured pace, producing fewer but more massive stars than gravity alone would create. The result, a more efficient, regulated stellar assembly line. Observations of molecular clouds support this. Regions with stronger fields show more orderly, filamentary structures, while weakly magnetized clouds collapse into chaotic, clumpy messes. Magnetic fields also play cleanup crew after stars are born. When massive stars ignite, their fierce radiation and stellar winds blast surrounding gas away, but magnetism channels these outflows into collimated jets and bipolar lobes, like nozzles on a garden hose. These jets can span light years, carving cavities in interstellar clouds and triggering new rounds of star formation at their edges. Even dying stars contribute. When supernovae explode, they leave behind magnetized neutron stars whose fields shape their pulsar winds, while the blast waves themselves can amplify interstellar magnetic fields by stretching and compressing them like taffy. The true testament to magnetism's cosmic role lies in its persistence. Despite the violent turbulence of galactic environments, supernova shocks, galaxy collisions, black hole eruptions, magnetic fields endure, constantly renewing themselves through dynamo action. They're the ultimate recyclers, transferring energy from galactic rotation to microscopic particles and back again. Some theories even suggest that without magnetic fields, galaxies would lose their gas too quickly to winds and explosions, leaving them starved for star-forming fuel. What's astonishing is how such a faint force can shape something as vast as a galaxy. It's like discovering the subtle tension in a spider's silk guides the construction of an entire skyscraper. As telescopes grow more sensitive, we're finding magnetism's signatures everywhere, from the polarized glow of distant quasars to the twisted fields around supermassive black holes. Each observation reveals another thread in the invisible tapestry holding the cosmos together, proving that sometimes the universe's quietest forces leave the loudest echoes. Turbulence in interstellar space is nature's way of stirring the pot, keeping the cosmic soup from settling into a bland uniformity or collapsing into lumpy chaos. Picture a pot of boiling water where bubbles rise and churn the liquid in unpredictable patterns. Now scale that up to a vast cloud of gas light years across, where shockwaves from exploding stars ripple through the medium. Stellar winds carve out cavities like spoons dragging through foam, and the sheer rotation of the galaxy itself whips the gas into swirling vortices. This isn't just random motion, it's a finely tuned mechanism that shapes how and where stars are born. When a massive star dies in a supernova, it doesn't go quietly. The explosion sends shockwaves racing through nearby gas clouds at thousands of kilometers per second, compressing some regions while shredding others apart. These shockwaves act like cosmic whisks, injecting energy into the interstellar medium and preventing gas from collapsing too quickly under gravity's pull. Without this turbulent stirring, gas would fragment into far more stars than we observe, most of them small and dim. Instead, turbulence creates a Goldilocks zone for star formation. Not too fast, not too slow, but just right to produce the balanced mix of stellar sizes we see across galaxies. But turbulence does more than regulate star birth. It's also the universe's master mixer. When stars fuse elements in their cores and later expel them in winds or explosions, turbulence ensures these heavy atoms, carbon, oxygen, iron, and more, don't just clump where they're made. Instead, it spreads them evenly through the galactic disk like folding cocoa powder into cake batter. This process, called metal enrichment, is why later generations of stars contain more heavy elements than earlier ones. Our own sun owes its planetary system to this cosmic recycling program. The iron in Earth's core and the oxygen in our air were once scattered by turbulent winds from long-dead stars. The origins of interstellar turbulence read like a catalogue of cosmic violence. Supernova contribute, but so do the fierce winds from massive young stars, which can blow bubbles hundreds of light-years wide. Galactic rotation shears gas clouds into spiraling ribbons, while mergers between galaxies send tsunamis of turbulence through their combined interstellar medium. Even the gentle infall of gas from the cosmic web, the faint trickle of pristine hydrogen still feeding galaxies today, and stir things up when it plows into the galactic disk at supersonic speeds. Each source leaves its distinctive fingerprint. Supernova-driven turbulence tends to be chaotic and short-lived, while rotation creates more orderly, large-scale patterns. Astronomers measure this turbulence by observing the width of spectral lines from molecules like carbon monoxide. The more turbulent the gas, the more those lines blur, a telltale sign of atoms moving at different velocities along our line of sight. These observations reveal something surprising. Turbulence in star-forming clouds follows universal scaling laws, much like how whirlpools in water obey fluid dynamics, whether in a bathtub or an ocean. This suggests that despite the vast differences in scale, the same fundamental physics governs turbulence everywhere, from Earth's atmosphere to the heart of distant galaxies. What happens when the cosmic stirring goes wrong? Too little turbulence, and gas collapses into stars so rapidly it exhausts a galaxy's fuel reserves in a frenzy called starburst mode, leaving behind a red and dead elliptical galaxy with no new star formation. Too much turbulence and gas never gets dense enough to form stars at all, leaving a galaxy dark and sterile. The Milky Way sits in the sweet spot, with just enough stirring to maintain a steady star formation rate of about one sun's worth of material per year. The most fascinating aspect might be how turbulence links scales. The same eddies that shape giant molecular clouds also influence the birth of individual solar systems. When our own sun formed, the swirling motions in its parent cloud likely determined the orientation of the protoplanetary disk from which Earth eventually arose. In this way, turbulence doesn't just build galaxies, it sets the stage for planets and ultimately life itself. Far from being mere cosmic noise, it's the dynamic rhythm underlying the universe's endless dance of creation. Galactic cannibalism sounds like something out of a cosmic horror story, but it's actually one of the universe's most elegant growth strategies. Think of it as nature's way of recycling on a grand scale, where larger galaxies absorb smaller ones, not through brute force, but through gravitational seduction. The Milky Way, our cosmic home, is a prime example of this gentle predation. Over billions of years, it swallowed dozens of dwarf galaxies, their stars slowly dissolving into our galaxy's outer halo like sugar, blending into coffee. These mergers aren't the dramatic, explosive collisions we often imagine. Instead, they're slow dances where gravity patiently unravels the smaller galaxy, strand by strand, until its identity fades into the larger whole. What's remarkable is how these devoured galaxies leave behind ghostly signatures. Astronomers have mapped streams of stars arcing around the Milky Way, celestial breadcrumbs tracing the paths of ancient mergers. One of the most famous is the Sagittarius Stream, a ribbon of stars torn from a dwarf galaxy currently being absorbed by our own. Then there's Gaia Enceladus, the remnants of a galaxy that collided with the Milky Way nearly 10 billion years ago, contributing hundreds of millions of stars to our galactic halo. These stellar fossils are like paleontological digs for astronomers, revealing chapters of our galaxy's history written in starlight. The process showcases self-organization at its most patient. As a dwarf galaxy falls into a larger one, tidal forces stretch it into long filaments, a phenomenon called spaghettification. Stars closest to the larger galaxy feel stronger gravity and accelerate ahead, while those farther back lag behind, creating streams that can wrap around the host galaxy multiple times. Over eons, these streams disperse, their stars settling into randomized orbits that blur any trace of their origin, yet their chemical fingerprints remain. Stars from dwarf galaxies often have distinct compositions lower in heavy elements compared to homegrown Milky Way stars, allowing astronomers to identify them even after they've fully assimilated. This hierarchical growth isn't unique to the Milky Way. The Andromeda Galaxy, our nearest spiral neighbor, shows even more dramatic evidence of past mergers. Its outer halo is littered with stellar streams and globular clusters that clearly came from elsewhere. Some studies suggest Andromeda may have cannibalized galaxies as massive as our own Large Magellanic Cloud within the last few billion years. Even elliptical galaxies, those smooth, football-shaped giants, owe their existence to galactic cannibalism, their featureless appearances the result of multiple mergers scrambling stars into chaotic orbits. But why does the universe favor this growth strategy? The answer lies in dark matter's cosmic web. Smaller galaxies form along the faint filaments of this web, then follow those gravitational highways toward larger structures. It's an inevitable process, like rainwater trickling downhill into ever larger streams. The Milky Way sits at a gravitational crossroads where multiple filaments converge, funneling smaller galaxies into its waiting embrace. This isn't destruction so much as transformation, where galactic building blocks assemble into ever more complex structures over cosmic time. The most fascinating aspect might be what these mergers leave behind. Beyond stellar streams, they can deposit supermassive black holes into galactic centers, trigger waves of star formation, or even reshape entire galactic disks. Our own Milky Way's central bar, that thick structure of stars at its heart, may owe its existence to ancient mergers that stirred the galactic disk like a spoon in coffee. Even our solar system's position in the galaxy could be influenced by these events. Some theories suggest past mergers helped create the relatively quiet galactic suburb where we reside. Galactic cannibalism proves that growth in the universe isn't just about expansion, it's about integration. Every time a large galaxy absorbs a smaller one, it doesn't just gain stars, it inherits their history, their chemistry, their very essence. The Milky Way isn't just a collection of stars, it's a living archive, its halo filled with the remnants of galaxies that came before. As astronomers decode these stellar fossils, they're not just reconstructing our galaxy's past. They're reading the autobiography of the universe itself, written one merger at a time. Dwarf galaxies are the universe's original pioneers, small, scrappy systems that laid the groundwork for everything we see today. Picture the cosmos in its infancy, just a few 100 million years after the Big Bang. The first galaxies weren't the majestic spirals or glowing ellipticals we know now. They were tiny, faint clumps of stars and gas, no bigger than a fraction of our Milky Way. These dwarfs were the cosmic equivalent of wildflower seeds scattered across an empty field, each holding the potential to grow into something grander. What they lacked in size, they made up for in numbers, filling the early universe like fireflies in a vast, dark meadow. What makes these diminutive galaxies so special is their simplicity. Unlike their larger cousins with intricate spiral arms or bustling star-forming regions, dwarfs often have chaotic, amorphous shapes, cosmic doodles, rather than detailed blueprints. This messiness is a goldmine for astronomers. Studying them is like finding preserved fossils of the universe's childhood, offering clues about how gravity first pulled matter together. Their slow, inefficient star formation, sometimes birthing just one new star every few million years, mirrors the conditions that likely dominated the early cosmos before galaxies grew sophisticated enough to produce stars in rapid bursts. Yet not all dwarf galaxies share the same fate. Some, like the large and small Magellanic Clouds orbiting the Milky Way, are locked in a slow gravitational dance with their larger host, destined to eventually merge and contribute their stars to the galactic halo. Others, like the isolated Leo T dwarf galaxy, drift alone in the cosmic void, untouched by larger neighbors. The difference often comes down to location. Dwarfs born near the dense filaments of the cosmic web, the universe's gravitational highways, get funneled toward galaxy clusters where they're absorbed. Those forming in the sparse voids between filaments may never encounter a larger galaxy, remaining pristine time capsules of the early universe. The survivors teach us surprising lessons about dark matter. Many dwarf galaxies are so dominated by this mysterious substance that their visible stars seem like afterthoughts, floating in vast halos of invisible mass. Some, like Dragonfly 44, are nearly invisible, their starlight so faint that astronomers only discovered them by tracking the motions of the few visible stars, revealing the gravitational grip of their dark matter. These ultra-diffuse galaxies challenge our understanding of how dark matter and gas interact, suggesting that the recipe for galaxy formation is far more flexible than we once thought. But the most profound revelation is how these tiny systems built the universe we know. Over billions of years, gravity drew dwarfs together like beads on a string, their mergers creating ever larger structures. Our Milky Way likely began as dozens of these small galaxies colliding and combining, their stars and dark matter blending into a single, grander system. Even now, this process continues. The Gaia spacecraft has spotted stellar streams in our galaxy's halo, the shredded remains of dwarfs currently being absorbed. Each merger leaves a chemical signature, enriching the Milky Way with heavier elements forged in the dwarf stars. The lingering question is why some dwarfs stopped evolving while others grew into giants. The answer may lie in their environments. Dwarfs that formed near regions of intense early star formation may have had their gas stripped away by ultraviolet radiation, stunting their growth. Others, perhaps those with slightly denser dark matter halos, held onto their gas longer, allowing them to grow through repeated mergers. It's a reminder that self-organization isn't just about rules, it's about opportunity, timing, and a bit of cosmic luck. Today, dwarf galaxies aren't just relics, they're active participants in the cosmic story. Some, like the recently discovered feeble giants, challenge our definitions of what a galaxy even is. Others host mysterious phenomena like the tiny triangulum Roman II, where gamma-ray signals hint at dark matter annihilations. Whether as building blocks, survivors, or laboratories for exotic physics, these faint systems prove that in the universe's grand design, even the smallest players can hold the biggest secrets. Galaxies are the ultimate recyclers, running cosmic factories where nothing goes to waste. When a star like our Sun reaches the end of its life, it doesn't just vanish, it gently exhales its outer layers into space, sprinkling the surrounding gas with carbon, nitrogen, and oxygen. Massive stars go out with even greater fanfare, exploding as supernovae that blast iron, gold, and uranium across light years. These stellar farewells aren't endings, but transformations, returning processed material to the galactic ecosystem like trees, dropping nutrient-rich leaves onto forest soil. This interstellar compost then becomes the raw material for new stars, planets, and potentially life itself, weaving an unbroken chain stretching back to the universe's first generations. Spiral galaxies like the Milky Way are recycling virtuosos, their orderly disks making the process remarkably efficient. Here, dying stars enrich the same neighborhoods where new ones form, creating stellar generations with increasing heavy element concentrations, what astronomers call metallicity. The Orion Nebula showcases this beautifully. Its glowing gas clouds contain debris from ancient supernova, now fueling a fresh wave of star birth just 300 light-years away. This proximity between stellar graveyards and nurseries allows spirals to maintain near-constant star formation rates for billions of years. Their delicate balance resembles a thriving metropolis where waste management systems perfectly match the population's needs. Nothing is squandered, nothing accumulates unnecessarily. Elliptical galaxies tell a different recycling story. These football-shaped giants exhausted most of their gas long ago during violent merger events, leaving them with aging stellar populations and little raw material. Yet they're not entirely dormant. Observations reveal faint traces of heavy elements in their sparse remaining gas, evidence of past recycling, now running in slow motion. Some ellipticals even harbor mysterious reservoirs of cool gas near their centers, possibly replenished by the gradual evaporation of old stars or the occasional cannibalization of smaller galaxies. It's a far cry from the vigorous cycles of spirals, more like a retirement community quietly repurposing heirlooms rather than a bustling industrial hub. Dwarf galaxies operate at the extremes of cosmic recycling. Isolated dwarfs like Leo recycle their meager gas supplies with painstaking slowness, forming only a few new stars per century. Their low gravity means supernova explosions can eject material entirely, starving future generations like a campfire repeatedly blown out by its own sparks. In contrast, dwarfs orbiting larger galaxies face brutal recycling conditions. The Magellanic Clouds, for example, are currently having their gas stripped by the Milky Way's gravity, creating a spectacular bridge of material between them while compressing remaining clouds to trigger frenzied star formation. These turbulent conditions produce starburst dwarfs like Henai's 210, where recycling happens in explosive bursts rather than steady cycles. The ultimate recyclers may be the universe's most energetic galaxies, quasars. Powered by supermassive black holes, these luminous behemoths blast out winds at nearly light speed, ejecting gas that might have formed billions of stars. Yet even this apparent waste serves a purpose. These outflows travel so far that they eventually cool and fall back, seeding future epochs of growth. Simulations show quasar winds can loop back after hundreds of millions of years, like cosmic boomerangs carrying enriched ingredients for new stellar recipes. This reveals recycling's grandest scale, not just within galaxies but between them, as the universe continually remixes its material across space and time. What's astonishing is how this cycle mirrors life's essential processes. Just as Earth's water circulates between oceans, clouds, and rain, galactic material flows between stars, gas clouds, and the interstellar medium, except on timelines stretching billions of years. The oxygen we breathe, the calcium in our bones, even the gold in our jewelry were all forged in ancient stellar furnaces, scattered across space, and eventually incorporated into our solar system. We're not just observers of galactic recycling, we're its products, living proof that the universe knows how to turn stardust into something wondrously new. The Milky Way isn't just our galactic address, it's a living laboratory where the universe's self-organizing principles unfold before our eyes. Every spiral arm, every star cluster, even the faintest wisp of interstellar gas tells a story of transformation, where chaos gradually gives way to intricate order. Take those iconic spiral arms, for instance. They aren't rigid structures but dynamic density waves, cosmic traffic jams where stars and gas pile up like cars slowing in a highway bottleneck. These patterns persist for billions of years, not because the stars themselves stay locked in place, but because the wave moves through the galactic disk like a ripple in a pond, triggering bursts of star formation wherever it passes. The result, a self-renewing design where gravity and motion conspire to create permanence from flux. At the Milky Way's heart lies another marvel of self-assembly, the central bar. This thick, elongated structure of stars acts like a gravitational mixing spoon, churning the galaxy's inner regions and funneling gas toward the supermassive black hole at its core. Bars aren't unique to our galaxy, but they're far from inevitable. Simulations suggest they emerge naturally from instabilities in rotating disks like a pizza dough spinning too fast and developing a slight warp. Once formed, the bar becomes a galactic power player, reshaping orbits and redistributing energy until the entire system reaches equilibrium. It's a reminder that even the grandest cosmic structures arise from small, incremental adjustments. Surrounding this ordered disk is the halo, a vast spherical cloud of ancient stars and globular clusters that defies the galaxy's flatness. These halo stars are the Milky Way's elders, relics of its violent youth when smaller galaxies collided and merged. Their orbits resemble tangled spaghetti, a stark contrast to the orderly circles of disk stars. Yet this apparent chaos hides a deeper logic. Each stellar stream, like the Gaia Enceladus remnant, maps a past merger, its stars tracing the gravitational tides that shredded their parent galaxy. The halo isn't just a museum of galactic archaeology. It's proof that self-organization thrives even in destruction, weaving scattered fragments into a cohesive whole. What makes the Milky Way such a compelling case study is its ongoing evolution. Right now, in the Orion Cygnus arm, collapsing gas clouds are giving birth to new stars, while supernovae in the Perseus arms scatter heavy elements into the interstellar medium. Meanwhile, the Sagittarius dwarf galaxy continues its death spiral, adding fresh stars to the halo with each pass. These processes aren't isolated, they're threads in a single tapestry, each influencing the others. When a supernova shockwave compresses a nearby gas cloud, it doesn't just ignite new stars, it alters the galaxy's chemical makeup, which in turn affects future generations of stars and planets. The Milky Way's greatest secret might be how ordinary it is. Among the hundreds of billions of galaxies in the observable universe, ours is decidedly average in size, shape, and star formation rate. Yet this very mediocrity makes it invaluable. By studying its details, the distribution of its dark matter, the chemistry of its stars, the motions of its gas, we uncover universal truths about how galaxies assemble and evolve. Every time astronomers map a new stellar stream or measure the subtle warp in its outer disk, they're not just learning about our home, they're deciphering the universe's operating manual, one spiral arm at a time. Perhaps the most humbling realization is that the Milky Way isn't a finished product. In 4 billion years, its fate will intertwine with the Andromeda Galaxy in a collision that will reshape both. The orderly spiral we know will dissolve, its stars flung into new orbits, its gas compressed into explosive starbursts. Yet from this chaos, a new equilibrium will emerge, likely an elliptical galaxy, smooth and featureless. It's a reminder that self-organization isn't about preserving form, but adapting to change. The Milky Way's story, like all galaxies, is one of constant becoming, where every ending seeds a new beginning. Stars are the universe's oldest storytellers, each one a gleaming archive of cosmic history written in the language of light. When astronomers peer at a star, they're not just seeing a point of light, they're decoding a chemical fingerprint that reveals when and where it was born. Take HD 140283, a yellow giant near the Milky Way center. Its atmosphere contains barely any iron, a telltale sign it formed over 13 billion years ago when the universe was still a chemical desert. Stars like this are living relics from an era before planets, before heavy elements, even before most galaxies took shape. They drift through our galaxy like ancient mariners, carrying whispers from a time when the cosmos was just learning to organize itself. Galactic archaeologists piece together these clues like detectives reconstructing a crime scene. A star's motion tells where it came from, whether it's a native of the Milky Way's disk or an immigrant from a devoured dwarf galaxy. Its composition, measured by the subtle dips in its spectrum, reveals what kind of stellar nursery birthed it. Stars forged in the chaotic early universe, like HD 140283, are metal poor, their atmospheres nearly pristine. Younger stars, like our Sun, are metal-rich, their chemistry enriched by generations of supernova that came before. Together, these stellar generations form a timeline of galactic evolution, each cohort bearing witness to the Milky Way's growth spurts, mergers, and quiet periods. The most astonishing discoveries come from stellar streams, rivers of stars arcing through the galactic halo like celestial graffiti. These are the remnants of dwarf galaxies torn apart by the Milky Way's gravity, their stars unraveled into long, shimmering ribbons. The Gaia spacecraft has mapped dozens, each with its own distinct chemical signature. The Helmy stream, for example, orbits backward compared to most Milky Way stars, a clear sign it originated elsewhere. Its stars are richer in alpha elements, oxygen, magnesium, silicon, hinting they formed during an early epoch of rapid supernova explosions. These cosmic immigrants don't just add stars to our galaxy, they bring entire chapters of galactic history, rewriting our understanding of how the Milky Way assembled itself. Globular clusters are another treasure trove. These dense balls of ancient stars, some nearly as old as the universe itself, orbit the Milky Way like bees around a hive. Unlike stars in the disk, which formed gradually, globular clusters appear to have been born in single, intense bursts, cosmic snapshots of star formation conditions billions of years ago. Their chemistry is a time capsule. Clusters like M92 contain stars with almost no heavy elements, suggesting they formed before supernova had seeded the galaxy with metals. Others, like Omega Centauri, show multiple stellar populations with varying chemistries, evidence they might be the stripped cores of ancient dwarf galaxies. What emerges from this stellar detective work is a revelation. The Milky Way didn't grow steadily, but in fits and starts. Some periods saw violent mergers, like the Gaia-Enceladus collision 9 to 11 billion years ago, which thickened the galaxy's disk and triggered waves of star formation. Others were quieter as gas settled into orderly spiral patterns. The stars themselves are the record keepers, their motions tracing the gravitational aftermath of long-forgotten encounters, their elements encoding the life cycles of generations long gone. Even our Sun, a relative newcomer at 4.6 billion years old, carries traces of these events in its chemical makeup, a legacy written in the atoms that now form our world. The ultimate goal of galactic archaeology isn't just to reconstruct the past, it's to understand the universal rules of self-assembly. By comparing the Milky Way to neighboring galaxies like Andromeda, astronomers are finding surprising variations. Andromeda's halo, for instance, contains far more metal-rich stars than ours, suggesting it grew through more frequent mergers with massive dwarfs. These differences hint at how sensitive galactic evolution is to initial conditions, like how the same recipe can yield different cakes depending on slight variations in mixing. Every galaxy is both unique and familiar, a testament to nature's ability to create infinite diversity from a handful of physical laws. So when you look up at the night sky, remember, those stars aren't just lights in the void. They're historians, archivists, storytellers. Each one holds a fragment of the Milky Way's epic autobiography, waiting for us to decipher its secrets. And as we learn to read their language, we're doing more than studying our galaxy. We're uncovering the universal playbook for how chaos becomes cosmos, one star at a time. Computer simulations are the universe's digital playgrounds, vast, virtual laboratories where scientists can rewind cosmic history and press play on galactic evolution. Imagine building a model so precise, it can take the primordial soup of the Big Bang and fast forward 13 billion years to produce a perfect replica of the Milky Way. That's the ambition driving astrophysicists as they harness supercomputers to decode the secrets of self-organization. These aren't simple animations, they're mathematical time machines, crunching equations for billions of virtual particles to see how gravity, dark matter, and gas physics conspire to build galaxies. When simulations like Illustris TNG or Eagle generate spiral arms, stellar halos, and black holes that mirror real observations, it's like watching a cosmic jigsaw assemble itself, piece by piece, law by law. But crafting these digital universes is no easy feat. The sheer range of scales is mind-bending. A single simulation must account for the galaxy-spanning pull of dark matter halos, while also modeling the turbulent swirls of gas clouds light years across, like programming a video game where every pixel follows the rules of quantum physics. To tackle this, scientists use adaptive mesh refinement, a computational sleight of hand that zooms in on dense regions like star-forming nebulae while glossing over empty voids. It's the cosmic equivalent of a chef finely chopping vegetables while letting a pot simmer unattended. Even with these shortcuts, a single simulation can consume millions of CPU hours, often requiring supercomputers to run for months non-stop. The real magic happens when simulations clash with reality. Take the missing satellites problem. Early models predicted thousands of dwarf galaxies orbiting the Milky Way, yet we've found barely 100. This discrepancy forced theorists to rethink how small galaxies form, leading to discoveries about how supernova and dark matter interactions might suppress dwarf galaxy growth. Similarly, simulations once struggled to produce realistic disk galaxies without them turning into featureless blobs, until researchers realized the crucial role of stellar feedback. When virtual stars were programmed to explode and blow gas outward, their energy prevented galaxies from collapsing too quickly, allowing delicate spirals to emerge. These eureka moments reveal how simulations aren't just testing theories, they're actively rewriting them. One of the most striking successes came with the discovery of the galactic bar instability. When astronomers noticed many spiral galaxies, including our own, had central bars of stars, simulations showed why. Rotating disks naturally develop these structures over time, like a spinning pizza dough forming a slight warp. The models even predicted how bars act as galactic conveyor belts, funneling gas toward the center to feed black holes, a process later confirmed by telescopes. Yet puzzles remain. Current simulations still can't perfectly replicate the diversity of galaxy shapes or explain why some ellipticals have more young stars than expected. Each mismatch is a breadcrumb trail leading to deeper physics, whether it's the messy role of magnetic fields or the poorly understood interplay between dark matter and ordinary matter. The frontier now lies in zoom-in simulations that focus on individual galaxies with unprecedented resolution. Projects like FIRE feed back in realistic environments, model star formation down to scales of a few light years, capturing how stellar winds and supernova carve bubbles in interstellar gas. These high-definition runs reveal self-organization in action, showing how local processes like a single exploding star triggering a chain reaction of births scale up to shape entire galaxies. Meanwhile, machine learning is revolutionizing the field, with AI algorithms analyzing simulation data to spot patterns humans might miss, such as how subtle differences in initial conditions lead to spiral versus elliptical outcomes. So how close are we to the perfect galactic simulation? The answer lies in the growing harmony between digital and observational astronomy. When the James Webb Space Telescope peers at infant galaxies in the early universe, its findings feed back into simulations, refining their parameters. Already, models like Thesan can simulate not just galaxy formation, but also the cosmic dawn, the era when the first stars ionized intergalactic gas. As computing power grows and physics becomes more nuanced, we're inching toward a day when a simulation might spontaneously generate something as complex as the Milky Way's spiral arms or the Magellanic Cloud's distorted shapes without any manual tweaking. Until then, every flawed simulation is a stepping stone, reminding us that the universe's self-organizing brilliance is both computationally demanding and endlessly inspiring. For all the universe's brilliance at self-assembly, some galactic puzzles still defy explanation, like cosmic riddles scribbled in starlight. Take red and dead galaxies, massive systems that mysteriously shut down star formation billions of years ago. These cosmic burnouts shouldn't exist according to early models, which predicted galaxies would keep forming stars as long as they had gas. Yet telescopes reveal entire populations of them, their fuel tanks seemingly drained overnight. One leading theory points to supermassive black holes as the culprits. Their violent outbursts might have blasted away remaining gas like a cosmic leaf blower. But why do some galaxies suffer this fate while others, like the Milky Way, keep churning out stars at a leisurely pace? The answer likely lies in the delicate balance between gravity's pull and the explosive feedback trying to thwart it, a balance that tips differently in different environments. Then there's the enigmatic dance between galaxies and their central black holes. These gravitational monsters, weighing millions to billions of suns, are far too massive to form from collapsing stars alone. They must have grown alongside their host galaxies, feasting on gas during cosmic mergers. Yet observations show an uncanny correlation between black hole mass and a galaxy's bulge, as if some unseen hand synchronized their growth. How does a black hole know how big its galaxy should be? Some theorists propose a feedback loop. As black holes devour matter, they radiate energy that regulates star formation, preventing galaxies from growing too large. It's a cosmic thermostat, fine-tuned over eons, but recent discoveries of overweight black holes in small galaxies muddy this picture, suggesting the relationship isn't as straightforward as we thought. Polar ring galaxies add another layer of bewilderment. These rare systems feature a ring of stars, gas, and dust orbiting perpendicular to the main galactic disk, like a vinyl record with a hula hoop spinning around its edge. The best explanation involves galactic cannibalism. A smaller galaxy, swooping in at just the right angle, gets torn apart, its debris settling into this peculiar configuration. Yet simulations struggle to recreate polar rings without them destabilizing within a few 100 million years. The fact that we see any at all implies there's physics at play we haven't yet grasped, perhaps involving dark matter's invisible scaffolding or magnetic fields we can't yet measure. Even more perplexing are the universe's orphan star-stellar populations flung far beyond their galaxy's visible boundaries. Some reside in enormous, diffuse halos extending millions of light years, far beyond where current models predict stars should exist. Were they ejected by ancient mergers, or do they hint at a forgotten epoch when galaxies expelled material more violently than we've imagined? Every anomaly like this forces scientists to revisit assumptions, revealing how much we still don't understand about the universe's self-organizing algorithms. The next generation of telescopes promises breakthroughs. The Vera Rubin Observatory will scan the entire southern sky every few nights, catching galaxies in fleeting states of transformation. The square-kilometer array's radio eyes will trace cold hydrogen gas, the raw fuel of star formation, with unprecedented precision. And advanced simulations, powered by quantum computing and AI, may finally bridge the gap between the quantum weirdness of black holes and the galactic scales they influence. Each unsolved mystery isn't just a gap in our knowledge, it's a doorway to deeper principles, waiting to show us how the universe's creativity outstrips even our boldest theories. After all, if self-organization were fully understood, the cosmos would lose its greatest magic, the ability to surprise us. The Milky Way and Andromeda are on an inescapable collision course, two cosmic titans locked in a gravitational embrace that will reshape them both. Right now, Andromeda streaks toward us at nearly 300 kilometers every second, a silent bullet fired across 2.5 million light years. When they meet in about 4 billion years, it won't be the violent smash-up we might imagine. Galaxies are mostly empty space, so their stars will slip past one another like two flocks of birds merging midair. But gravity will weave them together over eons, their spiral arms stretching into long tidal tails before relaxing into a smooth, football-shaped elliptical galaxy astronomers dub Milky Way. This future galaxy will bear little resemblance to its parents, no delicate spiral arms, no gas-rich disk, just a golden swarm of aging stars orbiting in random directions. Yet this transformation isn't the end of self-organization, it's a new chapter. As the galaxies merge, their remaining gas clouds will slam together, triggering a fireworks display of star formation. For a brief cosmic moment, Milky will outshine its predecessors with newborn blue stars, but this frenzy can't last. With no fresh gas flowing in, star formation will sputter out, leaving the galaxy to fade like a dying ember. Even supermassive black holes, now gorged on merger-fueled feasts, will grow silent as their food supply dwindles. The universe's most efficient recyclers, stars, will still work their magic, though. Red giants will shed their outer layers, enriching the scant remaining gas with heavy elements, while white dwarfs and neutron stars silently accumulate in the galactic core like cosmic retirees. Dark matter, ever the unseen architect, will continue shaping Milky's destiny. The combined halo of both galaxies, a vast, invisible shroud, will dictate how stars redistribute. Some simulations suggest the merger could fling a few % of stars entirely out of the galaxy, creating a diffuse, stellar halo stretching millions of light years. Others might get hurled toward the center, feeding the growing nuclear star cluster around the merged black holes. Over trillions of years, gravitational interactions will smooth out any remaining irregularities, as relentless as ocean waves rounding pebbles on a beach. Beyond our local group, the universe's accelerating expansion will isolate galaxies like never before. Distant clusters, now visible in our telescopes, will redshift beyond detection as dark energy stretches space-time itself. Milky will eventually stand alone in its corner of the cosmos, its neighboring galaxies having vanished over the cosmic horizon. Yet even in this isolation, subtle self-organization will persist. Stars will gradually migrate toward the galaxy's core through dynamical friction, a slow gravitational shuffle where lighter objects transfer energy to heavier ones. Over incomprehensible timescales, this could lead to core collapse, where the densest central region becomes packed with stars orbiting at dizzying speeds. The most fascinating twist, this future might not be as dark as it seems. Recent theories suggest that even in a universe dominated by dark energy, gas cooling mechanisms we don't yet understand could allow trickles of star formation to persist in isolated pockets. Rogue planets' worlds flung from their stars during the merger might harbor subsurface oceans kept liquid by tidal forces or radioactive decay, and civilizations, if any survive, could harness energy from black holes long after stars fade. The universe's self-organizing principles won't vanish, they'll simply adapt, finding new ways to create complexity even as the cosmic landscape grows ever more still. Ultimately, galaxies remind us that change is the only constant. From the first tiny dwarfs to the coming age of giants, their evolution reflects the universe's unshakable drive to rearrange itself. Milky won't be an end point, just another step in a story without finales, where even in the distant future, gravity, dark matter, and the remnants of stars will keep writing new chapters in the language of motion and light. Life emerges as the universe's most exquisite act of self-organization, a cosmic crescendo where stardust rearranges itself into conscious matter. The same forces that sculpt galaxies and stars might whisper through our very DNA, as if the universe encoded its architectural principles into biology itself. Consider the uncanny parallels. Galaxies arrange their stars into spiraling arms, while cells organize their components into intricate membranes and organelles. Both follow rules where simple interactions between parts give rise to breathtaking complexity, no master planner required. The branching patterns of nerve cells mirror cosmic webs. The pulsing rhythms of ecosystems echo the cyclical births and deaths of stars. It's as if nature discovered a universal playbook, one where self-assembly reigns supreme across scales. At the heart of this idea lies a radical shift in perspective. Life isn't an accident, but an inevitable flowering of universal tendencies. Take the humble lipid molecule which spontaneously forms bubbles in water, a precursor to cell membranes, or the way amino acids, bathed in ancient tidal pools, linked into chains without guidance, laying the groundwork for proteins. These aren't random chemical quirks, they're manifestations of matter's innate drive to organize, just as gravity hurls scattered gas into stars. Even the genetic code behaves like a cosmic algorithm, where simple base pairing rules generate endless biological innovation. The same physics that aligns galaxies along dark matter filaments might also guide proteins to fold into precise shapes, as if the universe thrives on recursive patterns. Ecosystems amplify this theme. A rainforest with its layered canopy and symbiotic networks operates like a galactic disk, each species occupying a niche as stars do orbits, their interactions maintaining equilibrium. Ant colonies build sophisticated tunnels without blueprints, much like gas clouds collapse into protoplanetary disks. These systems share a profound truth. Complexity emerges from the bottom up, governed by feedback loops where local actions create global order. A single termite doesn't comprehend the mound it helps construct, just as a hydrogen atom doesn't grasp the spiral galaxy it inhabits. Yet together they build wonders. Some theorists push further, suggesting life's origin was less a fluke and more a cosmic inevitability. The anthropic principle argues that universal constants, gravity's strength, the charge of an electron, are eerily fine-tuned to allow complexity. Tweak them slightly and stars wouldn't forge carbon or water wouldn't dissolve salts. In this view, the universe isn't just capable of life, it's pregnant with it, its laws predisposed to assemble matter into ever more intricate forms. Whether through deterministic chemistry or probabilistic trial and error, self-organization seems hardwired into reality's fabric, yet mysteries linger. If life is inevitable, why haven't we found it elsewhere? The Fermi paradox looms large. Where are the alien civilizations that cosmic logic suggests should abound? Perhaps life is common but intelligence rare, or maybe we're early arrivals in a universe still waking up to its creative potential. Alternatively, life might take forms so alien we fail to recognize them. Silicon-based ecosystems thriving in methane lakes, or electromagnetic beings dancing in plasma clouds. The universe's self-organizing brilliance likely extends beyond Earth's template. Ultimately, this perspective redefines our place in the cosmos. We're not passive observers, but active participants in a universe that organizes itself into consciousness. The carbon in our cells, the iron in our blood, all forged in stellar furnaces and scattered by supernova, now contemplates its own origins. In tracing how galaxies birth stars and cells divide, we're deciphering a deeper truth, that chaos and order are partners in an eternal dance, and life may be its most enchanting step. Whether alone or amid a galactic community of minds, we're proof that the universe doesn't just build, it wonders, explores, and remembers. Humanity's existence is a fleeting whisper in the universe's grand symphony, a momentary spark in a cosmos that's been organizing itself for 13.8 billion years. Every breath you take contains oxygen atoms forged in the hearts of long-dead stars, while the iron coursing through your veins was once the core of a supernova explosion. These celestial ingredients didn't just randomly stumble together. They followed the universe's silent algorithms: gravity pulling stardust into planets, chemistry arranging molecules into life. We're not just observers of cosmic self-organization. We're its living products, walking proof that chaos can give rise to consciousness. Consider the scale of our insignificance and our astonishing rarity. The Milky Way alone contains up to 400 billion stars, each potentially hosting planets. Yet across this unimaginable vastness, we've found no other example of life reaching our level of complexity. This paradox cuts to the heart of our cosmic identity. We're simultaneously inconsequential, a speck on a speck orbiting a mediocre star, and profoundly special, the universe's way of understanding itself. The same gravitational dances that shaped spiral galaxies also guided asteroids to deliver water to early Earth, while the self-organizing properties of carbon allowed simple molecules to evolve into thinkers and dreamers. Our growing understanding of the cosmic web reshapes what it means to be human. Ancient cultures saw gods in the stars. Today, we recognize that we're made of stars. The calcium in your bones was likely synthesized in a red giant's final throes, while the gold in jewelry originates from neutron star collisions so violent they warp space-time itself. These aren't poetic metaphors, they're chemical facts written in every cell of your body. Even our planet's position reflects cosmic architecture. Nestled in a quiet spiral arm between major stellar nurseries, we enjoy enough stability for life to flourish while still benefiting from nearby supernova that enriched our corner of the galaxy. Yet this cosmic perspective also highlights our fragility. The self-organizing processes that birthed us care nothing for our survival. A nearby gamma ray burst, a wandering black hole, or our own sun's eventual expansion could erase everything humanity has built. Paradoxically, this awareness fuels both humility and determination. We're temporary custodians of stellar legacy, tasked with preserving the rare complexity we embody. Perhaps this is why we explore space, not just to satisfy curiosity, but to honor the universe's gift of self-awareness by extending its reach. The most profound revelation may be how our consciousness mirrors the universe's creative drive. Just as galaxies form through local interactions governed by universal laws, human culture emerges from individual choices shaped by shared principles. Cities grow like galactic clusters, ideas spread like supernova shockwaves, and our collective knowledge self-organizes into ever more complex patterns. In trying to comprehend the cosmos, we're continuing its deepest tradition, turning chaos into meaning, one thought at a time. So what does it mean to live in a self-organizing cosmos? It means recognizing that we're both participants and witnesses in an unbroken chain of transformation stretching back to the Big Bang. The hydrogen that fueled the first stars now powers your thoughts. The gravity that shaped spiral arms now guides our spacecraft. Our existence isn't separate from universal processes with their latest iteration, the cosmos becoming aware of itself. And as we peer deeper into the void, mapping dark matter and decoding galactic evolution, we're not just studying the universe. We're its growing pains, its adolescence, its next creative leap, proof that self-organization doesn't just build galaxies, but sometimes, against all odds, builds minds to marvel at them. From swirling gas clouds to glittering galaxies, the universe is a master of self-organization. Imagine the cosmic equivalent of a child's building blocks scattered across a playroom floor, except these blocks are trillions of tons of hydrogen gas, dark matter halos, and newborn stars. Left alone, they'd remain a chaotic mess, but introduce gravity's patient pull, dark matter's invisible scaffolding, and the subtle push of magnetic fields, and suddenly, those scattered pieces assemble themselves into spiral galaxies, star clusters, and planetary systems of breathtaking precision. This isn't magic, it's physics in its purest form, where simple rules applied consistently over billions of years create complexity beyond anything human engineers could design. The real wonder lies in how universal these principles are. The same gravitational dance that shapes galaxies also governs the flocking of birds and the swirling of leaves in a gust of wind. Nature has a favorite blueprint, one where small, local interactions, particles attracting, stars exploding, gas cooling, scale up to produce global order without any central planner. Even our own bodies mirror this cosmic choreography. The calcium in your bones was forged in the hearts of dying stars, while the oxygen you breathe was once scattered across light years by supernova shockwaves. Every atom in your hand knows this dance intimately, having participated in the universe's grand self-assembly for billions of years before becoming part of you. What's humbling is realizing how much we're still discovering. Every time astronomers peer deeper into space with tools like the James Webb Space Telescope, they uncover new layers of this self-organizing symphony. Recently, we've spotted galaxies in the early universe that defy expectations, some too massive, others too structured for their age, hinting at gaps in our understanding of cosmic evolution. These aren't failures of science, but invitations to dig deeper, reminders that the universe's creativity outstrips our imagination. The same mysterious processes that birthed the first stars are still at work today, quietly shaping the cosmos in ways we're only beginning to grasp. This cosmic perspective transforms how we see our place in the universe. We're not just observers of this grand design, we're participants. The same forces that arrange galaxies into delicate spirals also guide the neurons firing in your brain as you ponder these very ideas. When you look up at the night sky, you're not just seeing distant lights, you're gazing at your extended family, stars and planets made from the same stardust as you. And just as galaxies grow through collisions and exchanges, human knowledge expands through shared ideas and collective curiosity. So where does this leave us? With a profound sense of connection to each other, to the stars, and to the unseen processes weaving order from chaos, the universe doesn't just build galaxies, it builds wonder, and we're here to witness it. Whether through a backyard telescope or a space probe's images, every glimpse outward is also a look inward, a reminder that we're the universe's way of understanding itself. Keep exploring, stay curious, and never forget, you're not just made of star stuff, you're the cosmos.